So how do you identify the most stable canonical structure? Canonical structure is just like resonance structure that we were talking about in a canonical form. Alright, one thing is that structures that are more stable, structures with more covalent bond, are more stable than the one with charge. Are you okay with that? So they are more stable than the one with charges. So two, stability is decreased by increase in charges. So stability decreases by increase in charge. What do I mean by this? For example, look at this guy. I can move this one here. So move this one here. So if you see, they ask you that which one is more. This one is going to carry positive charge. Are you okay with that? Then see double bond here. Are you okay with that? So this one carry positive. So between this and this, which one? This is one. This is two. Which one is more stable? So this guy is more stable now because it's covalently bonded. It's better than charges. So three. If the one with that obey octet or duplet rules are the most stable. For example, CH2C double bond C H to Cl. This is how it ought to be. Are you okay with that? So this is one. Alright. So if you see the movement, right, this one is coming down to this side, while this one is coming here. So you're going to have something like this. You're going to have like CHC minus AB, then C single bond CH, double bond Cl. This does not actually obey octet because this one is having double bonds. Normally, chlorine should not have double bond like that. Normally, on the normal terms, shouldn't have double bond. So it's going to carry plus here. So chlorine cannot have positive charge. So this is more stable than this. So this is the most stable one. Is more stable. Also, if you have this one between this and this, we have CH2C, alright, minus and double bond CH, then Cl. So this is wrong. So there's no name. So this is the most stable. Alright. So that is the most stable. How to identify? Yeah. So we are still on that how to identify. So the fourth rule is the electron, if the negative charge is on the negative atom, that will make it more stable than the one without. For example, you have H2C minus, then C double bond O, then H. So you might be thinking that if you do the resonance, so this one is coming down to this side, while this one moves, so that you can have H2C double bond C, then O minus. Okay, so this is one, this is A, and this is B. B is more stable. So this is the more stable between the two. So B is more stable. So let's talk about types of resonance effects. So we've done type of resonance effect. We'll talk about the most stable resonance effect. Alright, so we have the when electron is away from a group of the resonance effect is either plus R or plus M. So when electron is taken away from, let's say when the electron was taken away from the let's say for example, you have this one become double bond Abi. Look at the ammonium we had the other time. When electron was taken from nitrogen, nitrogen becomes what? Positively charged. Can you remember that? So that is that about that. So when the electron is the listen is taken to, where electron is taken to a particular source, it becomes minus. Let's say for example minus NH2 minus OH. Are you okay with that? So when electron is taken, also when the displacement is towards the group, so when electron is moving towards the group, so that makes it to be negative. So application of resonance effect, it is used to determine and explain the relative stability of reactive intermediates. It is used what? To determine and explain relative stability. Let's say stability of intermediates. So like what we did the other time. So which one is more stable between the two? Alright. So that is that about that. So let's talk about bond cleavage. We've been using it since morning actually. So there is always two particular bond cleavage. You know, for every organic reaction, it involves breaking of bond and formation of a new bond. Reactant is breaking bonds to form the product. Breaking of bond, formation. Breaking of bond and formation. So we have two classes. We have the homolytic cleavage and heterolytic. When we say homolytic, in homolytic it involves using of half-headed arrow, half, not full. Heterolytic, full-headed. For homolytic you have radicals. So for example, let's say you have R to R. This one breaks here, this one breaks here. Half-headed, so you have two radicals. Okay. For heterolytic, let's say you have R to X. It can break like this to form what? R plus what? So in heterolytic you have formation of ions. For in homolytic we have formation of radicals. Are you okay with that? So the most radical species is radicals actually. So let's talk about the hydrocarbon free radicals. Free radicals, a free radical is an atom or group of atoms possessing just odd or unpaired electron. So the radicals are from a molecule by homolytic cleavage. So Greek word the same. So let's say X to X, alright. So this one. So you have X radical plus X radical. So that's one thing you have to take note of. So the relative order of stability of radicals as follow. Alright, benzylic radical is more stable. The benzylic, when you say benzylic radical, this is benzylic radical. Sorry, just single bond. Benzene, is methyl phenyl. So the benzylic radical is more stable than allylic radical. This allylic, this is benzylic radical. So which is more stable than tertiary radical? Okay. Radicals are actually not stable, but so you get now secondary radical which is greater than methyl radical and so on. You get what I'm talking about like that. So this is the most stable, followed by allylic, followed by this. If you do the resonance, you see, the higher the resonance structure, the more stable a compound is. The higher you can get resonance, the higher the number of resonance hybrid, the higher the number of resonance hybrid, the better or the more stable it is, the compound is. So you can just, if you write the resonance structure of this compound, you get what I'm trying to talk about. But don't worry. So let's talk about the carbocation. So we talk about radical. In cleavages that we talk about, we have the homolytic, we have heterolytic. In homolytic we talk about it. We won't talk about the heterolytic now. The carbocations, the carbonium ions or carbocations. Alright, so let's say you have the benzylic radical. So we just have, okay, this is how it is, alright. It's carrying positively charged. So the more you have, I told you that alkyl group are suppliers of electron.
All right, they are negative. They are positive inductive effect to the supply electron. For our last class, I told you that. So when you have more alkyl group on a carbocation, it makes it to be more stable. Which this one is more stable than you have this allylic. The same thing with what we just did. Okay, which is greater than having tertiary. Okay, carbocation which is greater than having secondary, and so on and so on. Like we just did now, the same pattern. Are you okay with that? So the method of generating carbocation from heterolytic cleavage or by addition of a proton. When you add a proton to a substance, for example, if you have C double bond C and you add a proton plus H plus, so it can pick up this. We are still going to talk about this actually. So it pick up this. This one is carry plus. Okay. Are you okay? It's carrying positive charge. It has increased. If you added a proton to the compound, that's why it's like this. That is how to generate carbon. So let's talk about carbanion. Carbanion, that is R minus. This carbocation R plus or C plus, anyone. C plus or C minus, anyone. So the carbanion is a species. It's negatively charged already, it's full of electron cloud. So what's the trend? The trend is just opposite of this. The relative stability is just that you have the benzylic, alright, benzylic CH2 minus, okay, because of the resonance of this guy. Normally we actually need higher stability than other because of the resonance. It makes it to have higher. So than CH2, the alright, so which is greater than. Are you okay with that? So stability is opposite of what we are doing the other time, which is greater than the CH3 plus. Okay, so you get what I'm talking about, because it's electron rich. To pattern supply electron C compound here to make it to be less, so which is more greater than having R. This is more greater than having two R's. So this is primary, secondary, which is greater than the tertiary carbocation. You get now? So this one is more stable than the rest. This and this are almost the same thing. Why is this one higher? That's always been the contention, bone of contention actually. So it's always like that most of the time because of the resonance stability. Resonance will actually high to where. So that is that about that. There is a question here between CH3 plus and CH3 minus. Which one is the most stable? This is, what is this? So between these, so CH3 is the most stable because there is no charge on it. It always levels. Anyhow, where is it? You put star. Oh, this star. We'll talk about the benzylic and allylic structure species, the radicals. So how did they move and go? So we'll talk about that. The chemical structure of benzylic species. For example, look at this, the allylic species that we have the other time. So let's say you have this radical, this one come to this side, this one come here. You can do the resonance structure so that you can have this. So no, we've not talked about the so we didn't talk about this radical resonance the other time. So this is just the same thing like that. So for the canonical suballylic species, so for the other one, for the carbocation, you can have it this way. So this moves to this side so that you can have I told you that it's because of the resonance structure. That is why for the minus, that is
There's an error here. So you have negative charge. You can come to this side where this one moves here. So that is that about that. For the benzylic radical,
So I'm a benzylic radical, benzylic stuff. We talk about that in next class. So we'll talk about that in the next class. So we have steric effects. This ability of electron may be modified or even nullified by the influence of steric effects. Steric factor are the what we call degree of bulkiness of group around a particular atom or species in the organic compound. So effect of delocalization of p electron can only take place in pi or p orbitals on the atoms involved in delocalization, can become parallel or fairly nearly so. If this is prevented significantly by overlapping, cannot take space and delocalization may be inhibited. This hindrance mostly due to the presence of bulkiness of group. So we call it steric hindrance. We call it what? Steric hindrance. We call it a steric hindrance. So steric hindrance is just like having the bulkiness of group around a particular atom. Let's say you have R to R, R to R. Now CH, R to. So maybe you want to do movement of piling. You want to move this array, or you want to add something to this guy because of the bulkiness of group. If any reaction is coming, you can't say you want to attack this guy. You can't say you just want to remove this one and something here will now come here. No, it won't go that way. What happens is there will be a shift. This one can now shift to this side so that this guy will be less prone for the attack. You get what I'm saying now? Bulkiness of group also determine the way reaction proceed. It's very, very, very important. So let me quickly do the free radical, the benzylic, the reason why they are more stable, the benzylic structures or species in radicals and also in cation and anion. So for the radicals, you have this. Alright, this is CH radical. You have a bond here, you have a bond there, you have a bond there. So when radical comes, half arrow, this one too, half arrow. So this one will come to this side, half arrow. So you have this for structure. So that's why I said they are more stable because of the increase in number of resonance. So here, that means you have CH2, alright. Here you have a radical. So don't forget you still have this, and you have this here. So this radical too can continue here. This one too can come down to this side. This one too will come here. Look at the how far we are moving on. So this one too will come. So you have another hybrid resonance. This. This is where you are moving now. So that will be double bond there. That will be double bond there is here already. So this is the first you get now. So this one is coming down here as a radical. Don't forget you still have this here. Alright, so this one too can come down to this side. This one too will come here. Why? The remaining bond will come down to this side. So you have another radical. Sorry, you have another hybrid orbital. So this guy, double bond CH2. So that is why they are stable. So you have the here and you have a radical here. So continue, you can continue until you have. So you can still continue. This one will come down to this side. This one will come here. This one will go back. So you can have this here, this one here, and the out of this, sorry, the one is coming down to this side, the other one is going up. So you have this again, this happy, and this CH2, this back. You get the logic now. So that is for the radical species. For the R plus species, where it's full headed arrow, you are going to move. So you have CH2 plus, you have this here, you have this here, you have this here. So how is it gonna be? So the bond here will move to this side. If the bond here moves to this side, you have this here.
plus abi. So this one will come down to this side full headed. Double plus here. So you still have double bond here. So this one can move here so that you have this. Alright, so this one can come back. So you have this. So that is for the negative part.
For the carbon ion,
For the carbon ion, you have so this guy can come here. Why this one will move here? So you have this. So this one can come down to this side. Why this one will move? So this one can come here. Why this one will move here? So this one can come here. Why this one will move? So you have what you have started with back. So that is that about the movements and the stability, why they are stable. So steric hydrants is another factor. We've talked about what is electronic factor. Steric factor is another one. So I've mentioned it from the beginning. So so that is that about that. Okay, so we solve between decide between this guy and this guy. Sorry, and this guy. So which one is more stable? Alright, so that is that about that. Between this and this, which one is more stable? Between this and between this and between this and this, which one is more stable? And between this and this, which one is more stable? Okay, identify the most stable, the one will be more resonance stabilized between these days. Between this, alright. One. Between this and between this two and three. So that is the work. We know that this one will be more stable. Alright, we believe this one will be more stable. We expect this one to be more stable than the other one. So between this and this one is closer to this, so there can be resonance structure here. So this one is more stable, this one should be more. Then this one of negative charge, we expect this one to be more because this one can still be the electron to inside. So that is that about that. Thank you. We see the next class. So you can just juxtapose what we've done
and God bless. Thank you.